Thanks for joining. So reading groups is just like a small group of people. We look at the papers every week. And last week we covered just your standard NLP stuff, LSTMs, ordinance, seek-to-seek, and transformers. I was doing a bit of recap of transformers before diving into everything else. This is our outline for today. First, I'll have a recap of attention. And last week, someone suggested we do something hands-on, so we have notebooks this time. And if you want to follow along, you can go to my GitHub and clone my repo. There are a few Jupyter notebooks on there. You can also download the weights from Google Drive. I have the links on Discord in the reading group channel. We'll look at BERT, which is, I guess, our main focus today. We'll also look at GPT. GPT came before BERT, I think. We're going in that order. And then we'll do another BERT classification notebook. And if we have more time, we'll look at the efficient transformers. Cool. So last time we talked about transformers, and transformers are essentially made of a lot of attention blocks. And when we talk about attention, usually we think about this matrix. So the words on top are, I guess, the input words, and the words on the left are kind of the output words. We call the input words queries and the output words keys. And between each query and key, there's this matrix called the attention matrix, or I guess similarity matrix. And the brighter the cell is, the more similar they are, and the more important that specific token is to the output. So like we said last time, this is English to French. Usually it's just the English words correspond to the French word, except these two words, which are reversed from English and French. So we talked about the input words being queries. Usually just multiply the input tokens with a trained weight called the query weight. And we multiply the output with the weight of the keys to generate a key value. And then there's also a value that we multiply input with weights with. And this is the attention formula, I guess. It's just a dot product of current key, normalize it, and we multiply value into it. And some people call the transformer attention as dot product attention because of this operation. Blah, blah, blah. Oh, okay. So input words, there are a few ways of converting it. So usually they are just, each words correspond to a vector. So for example, the first word in the vocabulary can be 1000, second word would be 0100. And then there will also be an embedding layer in the transformer model to help with making it less, making it more decimal, making it a layer that we can actually train with, if that makes sense. We'll also talk about embeddings later in BERT as well, because they deal with embeddings slightly differently. One thing that we'll be focusing a lot on today is the efficiency of a transformer. And the base transformer itself is actually not very efficient, because if we think about it, I think this sentence has around 15, 16, 17 words maybe. For a sentence of length 17, we would need a matrix of 17 by 17. So that's ON squared memory requirement. And these numbers get stacked really high really quickly. So that's why a lot of transformer the base transform model usually only takes up to a maximum of around 512 words. And if you go any higher, you would need more hardware, and that kind of sucks. So today we might be going into some efficient transformers and how, and I guess what they do to mitigate this problem. So we'll look at a notebook that is mainly copied from the PyTorch tutorial. And if you want to follow along, it's on GitHub, and it's in the reading group channel. So this is just base transformer model. We're using PyTorch as the main library for doing this. The data set is also from PyTorch, from Torch text. And today we're gonna deal with machine translation. We will be translating from English to French. So we're taking the IWSLT dataset, and we're using the 2016 version because this 2017 version doesn't have French. So I wanted to do French, so we're using 2016. Tokenizers. We're declaring two tokenizers. One is for French, one is for English. And basically what a tokenizer does is it splits a sentence into words and punctuations. So hello there would be hello there in general, plus the punctuation. You would see that we're declaring a few special values here. We'll be introducing even more in BERT, but for transformers, the main main special tokens that we'll be using are the unknown tag, the beginning of sentence tag, the end of sentence tag, and the padding tag. So for each word that we don't know, we'll be appending unknown tag to the sentence. For each sentence, we'll be using a beginning of sentence tag to precede the sentence, and for end of sentence, we'll put an end of sentence tag. And padding are usually used for if you want to pad a sentence to the maximum length. So we can use it, we can throw it in the model. And these end of sentence tags are useful because when we do translation, every time we generate a word, if we don't have these end of sentence tags, I guess it will just keep generating. But if a model outputs an end of sentence tag, we can stop generating predictions. So there's a nifty function from Torch text that builds vocab from an iterator. It does exactly what it says. You have an iterator here of the trained data set plus the tokenizer. And then you just build English vocabulary out of it. And I did a minimum frequency of 10 because if I don't do that, there will be like, I think 60,000 words per vocabulary, and that's a lot of space for my small computer. Exactly the same thing, and then we can see that right now we have like 15,000 words for English and 17,000 words for French. This line is just flexing I have a GPU. It's not a great GPU, but it is a GPU. We'll go into here first. Obviously, like I said before, transformers can usually handle a max length of like 512, or in some transformers 1024, but my computer does not have a lot of memory, so I will do a max length of 60. These are just the data processing sections of the data processing section. So for each batch that it generates, so each batch would be a size of batch, and then the sentence. So we loop through each batch. Source, of course, means the English sentence. Target means French. We process the words. We know what a tokenizer does. It converts it into words, a list of words, and then for vocab, it actually converts the split words into a vector representation, and then we concatenate a beginning of sentence and end of sentence tag to those words in this function. And then at the end, we just pad the sequence right up to the max length. Okay. PyTorch has this module called transformers. I'm pretty sure it's relatively new. So that is the transformer. And since we're doing a machine translation task, we're gonna have to have a generator at the end of the model that has the target vocabulary size, which takes in, of course, the hint size. These two token embeddings are here. It's just a layer that a layer of trainable weights that embeds the words and turn them into slightly fuller vector representations of those words. That's just a normalization. Positional encoding is here. So it's basically doing this thing that we talked about last week. The two sinusoidal functions that denote the location of the word. So as you can see, this is the exponential calculation, and these are the sine and cosines. This notation tells the function to start from 0 and skip every other one. So it does the even ones, and this one does the odd ones. Because as you know, there's different functions to calculate if it's even/odd. And what positional encoding does is it takes the token embedding from this this function, and you add the sine cosine stuff to it, and you apply a dropout layer. You can of course append, like concatenate these two vectors, but then that would make the memory requirement of this model even larger, and I don't have that much memory. So forward, you embed it first, and then you positionally embed it, put it through the transformer, and generate the output. That's the PyTorch transformer. And of course, during training, for these two, they are not used until later when we have to actually translate those words after training. But in terms of training, we can just use this transformer. And not sure, transformer model. So last week, we mentioned that there is a masked multi-head attention, and that's what these two functions do. Basically, this function creates all the masks that you need in a transformer model. So this square subsequent mask is just hiding information that it does not know yet. So this is just an example. For information that the model shouldn't have access to, I would make the value negative infinity. And there are also padding masks, which basically tells the model not to bring any weights in that area because padding doesn't mean anything. Some basic parameter stuff, you declare the model, you initialize the weights. These two are kind of standard loss function optimizers that we use. And this is one train epoch. So for each training epoch, we declare the data set, we declare the data loader from the data set, and in the collate function, we pass in the data processing function. We create the masks first, and then we pass it into the model with all the masks and stuff. and then we just do a loss backward. And that's really it. And evaluation is basically the same thing, but with a different data set, which is the validation. And here is some of the training that I did, or that I already did. I'm not going to run it here because each one takes like 800 seconds. It'll take like over an hour to run this transformer model, but you can see that the loss is decreasing, which is great. And then the first sentence translating hello, how are you to French. This one is not great, but towards the end, I think this is good. I don't speak French, but I think this looks fine. This looks like French. For getting a translation, I'm using a greedy decoder. What a greedy decoder does is always takes the word with the best score in the next prediction. But there's also beam search, where for every word that it predicts, you choose the top N words, and you just kind of go through the sentence, and then at the end of the sentence, we see which combinations of words has the highest score. Yes, this is trained on English to French translation. I can actually, yeah. So this is each of the input and output sentence. So English words and then French words. Yeah, so if you want to play with it, I have uploaded the weights of this training to a Google Drive. You can download it, import it, and try to translate some words. Cool. So basically, BERT does not contribute much to outweight. Are there any changes that can be made to make the model more accurate? You can fine tune it like any other machine learning models. Yeah, it's maybe if you think that the translation is not capturing the, I guess, complexity of this language, then you can increase the amount of heads. So it's just changing these parameters, perhaps. So increasing any of these four would increase the model's ability to I guess understand data. I'm absolutely using way smaller numbers than the original transformer paper, so it's not great, but it works. So BERT doesn't actually contribute a lot more in terms of the model of a transformer. We are only using the encoder part of the transformer. And but what BERT brings to the table is the pre-training tasks that allow it to continue. So what it brings to the table is the pre-training tasks that allows it to understand the relationship between words and the relationship between sentences. We will first look at mass language modeling. Actually, one thing to note is that they pre-trained both of them at the same time. So mass language modeling. Basically, what this task is they take a large corpus of words, and then they mask out 15% of the words. And then the job of this model is to predict what word is in between, what word is masked, and output it. And what it does to the model is it trains it in a bidirectional sense. So it understands to look at the words after and before the mask to generate a prediction. And it is important to note that for each mask, not 100% of them are actually using the mask token. 80% of the time it is, but 10% of the time it's actually just a random token and 10% of the time we're using the original token of the sentence. And this is just to keep the model from keep the models learning and training the weights, because if we are masking out 15 of the words all the time, then the model might start to ignore the words at those positions, because, as you know, the actual masked token is not important. So this is just to alleviate the effects of those. So we have one sentence here that is masked and a second sentence that is masked here, and the output would have the actual correct word. And then next sentence prediction. The final goal of this task is to understand the relationship between two sentences. So it predicts whether one sentence immediately follow another. We have the same masked sentence and the same masked sentence B. So these two sentences, and the job of the model is to predict whether these two sentences actually follow each other. And you would see that there's a CLS token here. This doesn't actually do anything in terms of the input, but in the same spot in the output, we would generate the classification. So 1 would be the classification that sentence B follows sentence A. This is just to make the input and output the same size. And for each of these pre-training, you would see that we are using an embedding here. And this is actually slightly more complicated than just the usual embedding we see in words in transformer models or other models. We first take the usual ones that we use. So this is just a vector representation of these words separately. Why is this? Okay, this makes this sentence looks weird. Oh, is this the mask word? Okay, I think this might be the mask word. So there's a second embedding. This one is called the segment embedding. So this basically just separates the sentence. And these embeddings are also trainable. So this is kind of like a lookup table. The first sentence would all use the same embedding, and the second sentence would be all use the second embedding that we are training. Some papers have said this is useless, so some papers would not use it. We are also using positional embeddings. This is different from the transformer positional encoding because in transformers, the positional encoding is not trained, so it does not evolve over time, but this one does. This basically just you can imagine it as a lookup table. The embedding of the first token would always be in the same spot. You train it and use it for another sentence. And each position in the sentence would have a separate embedding. And then we add all three of these together to generate this input that we use in the BERT model. Last time I talked about Blue and why it's kind of not great for actually evaluating the translation of transformers. And so in this new thing, so they devised a different benchmark for evaluating text models. It's called Glue. It basically just takes the model and trains it on a lot of different tasks and then average out the score. And I think if you go to this website, you would see the different tasks and also, I guess, the leaderboard, I think. Some of the tasks that we're looking at for example, QQP is the Quora question dataset. It gives you two questions, and you will have to tell if they are similar to each other. QNLI is your standard question answering dataset. I'm pretty sure this is the same as Squad, but it's slightly more tidied. And COLA looks at grammar, like the grammar in a sentence. SST2 looks at the sentiment analysis, so your standard classification. And MRPC judges whether two sentences are expressing the same thing. So in here, we looked at pre-training, and this is just to get an understanding of the language that you're using. And after pre-training, we need to fine-tune it for different tasks. So for example, in a sentence pair classification task, this is basically the same usage as next sentence prediction. You put the first sentence here, second sentence here. You use a separation token in between, and then I'll put the classification in the first spot. Single sentence classification, slightly different. You basically lose the second sentence and the separation token. And you also have the classification in the first spot. For question answering, you put the question in the place where you put the first sentence, and a paragraph into where the second sentence should be. So a paragraph in this context would be, for example, if you're asking a question about mitochondria here, then the paragraph might be a page from Wikipedia about mitochondria, and the task is to highlight which sentence in that whole paragraph can answer that question, and this is what that outputs. And there's also the last one, which is you input a single sentence, and it'll tag each word as the part of speech in that sentence. It's 40 minutes. I'll just quit this call and rejoin. I'll see you later. I'll just start. So this is a pretty interesting paper about BERT used in a biological context. So if you don't know much about biology, all proteins are actually made up of a sequence of amino acids, and it can be viewed as a language. So each sequence of amino acid, which is a protein, it's kind of like a sentence, and each different type of amino acid is kind of like a word in the sentence. And there's actually only 20 amino acids in this world, so that makes it slightly easier for everyone. And so people decided to train BERT in protein classification. And then this paper basically just evaluates how the attention mechanisms work within these protein trained BERT. So it's important to note that these BERT models are not actually trained directly for any of these tasks that or any of these goals. They're trained to predict something else. I do not remember what it was for, but essentially it the authors in the paper think that it actually captures a lot of information that we did not intend to capture, but it's great that we captured. So on the right here, we have a substitution matrix. It actually just tells, it's just a standard matrix that they use in biology, and it tells you whether one amino acid can be replaced by another amino acid easily. And on the left here, it is the attention, the pairwise attention of these amino acids, and you can see that the activation, sorry, not activation, but the dark spots are kind of similar in both of these matrices. I find that pretty cool. So that's that. And there's also another thing that the authors discovered. So when they looked at the attention rate in a specific head, they realized that it actually correlates a little bit to how likely that two amino acids are going to be in contact within a protein. So when you have a sequence of amino acids, they don't just become a long string of things. They actually fold together. They become helices. They become like beta pleated sheets. And some amino acids are closer to each other than the rest. And basically, they find that in this head, they were able to predict whether they could be in contact without training, without specifically, explicitly training it to do so. So that's pretty cool. We'll go into a second notebook, and this time we're using BERT, and we're using the BERT from a Huggingface library. This time our task is to, oh yeah, it's pre-animated. This time we're looking at the fake news data set. I actually tried two of those data sets. The first data set does not work great because in the first epoch, it already has like an accuracy of 1, just terrible. So I found a more difficult data set to train on. And we're using the transformers library, which is from Huggingface. Blah, blah, blah. Encoding, decoding is basically the same thing, except this time we're using the tokenizer from transformers. And we declare a data set here. We are using a CSV that I downloaded from Kaggle. It can be found here in this link. Read the data set, and for each X file, we're just using the full text versus the label, and then we pass it on to the model. And this is the actual classifier. It's only like 10 lines of code. It's the Huggingface library makes it really simple to do all these stuff. So basically, you use a pre-trained model from BERT, and of course, you would use a pre-trained model because it's just text and it's in English. So you should use a pre-trained model. And then we're just applying a dropout layer plus a linear layer for classification. So n classes of classification. And once we pass some data into the BERT model, we're using only the polar output and applying a dropout plus the linear layer in that model. This is just standard querying stuff. And the Huggingface library provides the Atom W optimizer, which is, I think it is a slightly advanced version of the usual Atom optimizer that we use. It converges faster. And we're using the usual cross entropy loss. So just the usual stuff, we take the data, put it into the model, get the max out of it, put it through a loss function, and throw it backwards. It's just the same thing. And here we can see that it actually classifies these fake news pretty well. Yeah, there's like an 90-something% accuracy towards the end of Epic 4. As always, the weights are in a Google Drive folder. You can download it and use it later if you want. And this is just a confusion matrix of the data, of the test data. I think it's the test data. Yep, it's test data. If you don't know how to read a confusion matrix, these two spots are the ones that are supposed to be darker if you want a better model. So this is the true negative, true positive. And we can see that it's actually predicting very well with only like 30 something that are predicted wrong. Yep. Go back to. I think we'll have enough time to just cover GPT. I'm just going to move the efficient transformers to next week. So GPT. GPT is kind of the opposite of BERT. It basically just uses the decoder part of a transformer model. And if you were wondering what the difference between the encoder and decoder part of the model is basically just this block. So in a decoder, you would have a masked attention at the beginning. And kind of similar to BERT, it has a pre-training phase and then an actual training phase. And the main difference is that in the pre-training, in the actual training phase, so the fine-tuning phase, they still use the loss from the pre-training phase to continue to train it better. So loss 1 is all the tasks used in pre-training, and they multiply it by like a lambda term and then add it to the actual loss in the fine-tuning phase before back propagating it into the model. Sure, wrong button. And basically similar to BERT, they use a corpus of words to train this pre-training phase. And these are the tasks that the GPT were trained to do. Textual entailment is just predicting whether a hypothesis is a consequence of a premise. And we separate those two sentences with a delimiter of $. And I would send the link to the PowerPoint later, but if you click on the link, you would see kind of examples of what these premise and hypothesis are like, and you would predict whether it's neutral, contradiction, or entailment. It's kind of difficult to understand, I think. There's also the standard question answering set. So in a GPT, they would kind of input it this way. So you would have the question or context, and you will have to first answer it in a multiple choice. And you would do exactly the same thing for the second choice and for all the choices. And then you put them all through a linear layer, and we'll see which one has the best output. And the best output would be the answer. The Quora question similarity it's also used in, what was it called? Glue. It was used in Glue. And also classification, whether sentence is grammatical, also used in Glue. And that was the end of GPT. There's not actually a lot to cover for GPT. And I guess we'll have some time to talk about some of the efficient transformers. So like I talked about before, transformers are not exactly the most efficient models out there. And like, for example, the memory requirement is O(n) squared because of the attention matrix thing. And there's a bunch of papers that we'll be going through that kind of mitigates that problem. And this one does not exactly cover that problem, but we'll go through this one first. So in a transformer, there's a max sequence length of around 512. And basically what people before this paper does for long text is they split the text corpus into a few parts, and then they put it each through a transformer. So you can probably already see the problem right there. It's just the first corpus of words would not be correlated with the second, and you would also not have the information from the other corpuses when you're evaluating, for example, the third corpus of words, and that sucks. So there's two things that this paper introduces. The first one is sentence level, segment level recurrence. So basically, it's kind of like an RNN, where after you train the transformer model on this segment, it will keep the hidden state from this segment, and it will pass it on to the next transformer model. Kind of like an RNN. It's basically like an RNN. You're passing the hidden states from previous segments of the text onto the next, so you would have information from the previous texts. And actually using this makes it faster, 1,800 times faster in evaluation than your base transformer, because you're keeping these cached hidden states, so you don't have to do it again. And of course, that comes at a cost of memory. But I mean, evaluation, if you have an 1,800 times faster evaluation, I think it's pretty sick. Another thing that this model introduces is relative positional encoding. So usually when you split this text into a few sections, then it would say have a positional encoding of 0, 1, 2, 3. Would also have the same positional encoding of like 0, 1, 2, 3, 0, 1, 2, 3, but they are not actually like 0, 1, 2, 3 spots in that text, right? Because it's all a part of a larger text. So this paper introduces relative positional encoding. So basically all you care about between two words in corpus is number of words between it. And yeah, it's just the number of words between it. So here we have the attention score. You might see that it's very, very different from the attention score listed here, and that's because they broke it down. They broke it down into these 4 terms that we're looking at here. So just some basic terminology. E is embedding, W is weights, U is the absolute positional encoding used in transformer, so your sine, cosine, and this is basically your attention, but like split into 4 chunks. And with this model, with relative positional encoding, we are replacing all the U's with R, which is the relative positional encoding. And you might be wondering why we replaced UIWQ, the whole thing, with U and V, and that's because with relative positional encoding, the position of the first word actually does not matter anymore. You're only looking at the distances between them, right? So we replaced them with U and V, which are trainable weights. And this, according to this paper, helps learn the transformation. It helps learn the general position of these words. And the results of this paper is that using the same parameters, same hardware, you are able to learn 400% longer than normal transformers. So 400% of 512 is like 2,000 something words, which is a significant improvement from base transformer. It's obviously named in the same named after the Sesame Street character, and it's just something that machine learning people does. Someone named the first model BERT, someone named some model Elmo, and so the authors are like, okay, let's name this big bird. And what this model brings to the table is that, so in a basic transformer, their attention matrix is full. So all the boxes in this box would be filled, but Big Bird basically only uses some of the spots within that model. So for example, in window attention, it would only look at the words like a specific amount of words before and after your current token. And I think this one is just one word before and after. And then random attention is just for each word, for each query, you look at 2 or 3 other random words in the sentence. And also there's global attention, which is you append. So if you remember, the first few spots in a BERT model would be like CLS, which is not actually used. So they use those spots for global attention. And you might be wondering, first of all, why would random attention work when I guess 2 words in a sentence have to in some way relate to each other? What if they don't capture the meaning? And you might be wondering why they use global attention on words that don't actually matter. Well, so you can think of it like this. So let's look at this word here. So this first row would be one layer. This is the second layer, and this is the third layer. The first word would be the global attention. So each word in a sentence would have attention with it. So you can see lines going into that ball, and it will also go to every ball. And in the second one, we can see that the random attention goes to the third ball, which is the third word. So the intuition between random attention and global attention is that even if the second ball is not connected to the fourth ball, it can use the global attention to kind of step through and capture the attention between those 2 tokens. So yeah, you follow the red path and you can eventually reach there. And you can see that with global attention, this path is actually minimized, because if you imagine if it's only just random, maybe you have to traverse a few times before you can reach the token that you're trying to reach. but with global attention, the maximum steps is like 2. And the result of this is kind of like a sparse attention. It doesn't use all the memory that you're expected to use in your basic attention matrix. I think it uses a constant times n. So this is, I don't know, like 2n, 2n, and 2n, and then it'll add up to 6n. Those are not, I'm pretty sure it's not actually 2n, but that's just an example. Right? Okay, I'll just go through the rest. There's only like 2 papers left. They'll be short. Reformers. It introduces 2 new concepts. So one of the new concepts is local sensitive hashing. And basically, what it does is that it does not compute the attention between every 2 words in the sentence. So they use a hashing function, which is this function, to separate words into different buckets, and it'll just do attention within that specific bucket and the bucket right next to it. And it only goes that one way. And what this basically does is the same thing. It reduces the memory required for an attention function. Yeah, that's just a very basic high-level view. Oh, and another thing that this paper introduces is they use the same weight for both query and key. And if you remember from base transformer, they used weights for query and key, and they used same weight for both, and they did not see a significant performance drop. So they're like, good. And it reduces the memory requirement used in that model. That's reformers. They also introduced this new thing called reversible residual connections. So in a transformer model, if you remember, there's these feed forward path that takes the input and then add it right back there, kind of like a ResNet. So the authors of this paper found inspiration in a paper written for ResNet called RevNet. And basically, the original complaint for ResNet is that you will have to store all the activations between X's, and that's a lot of activations to store, and that just exhausts a lot of your memory. So like when you backpropagate, you have to know like X from here before you can backpropagate. So they decided to split the input into 2 chunks, and then to find the input of like right here, you would only have to subtract this function to get there, if that makes sense. And then to get from this point to this point, you only have to subtract the function f, which is basically what is set here. And basically the only thing that you would have to store is the final output plus these functions, which is in a way saving your memory, but it also increases a lot of your computational time. It takes up like 3 times the effort. So these are just all the equations used in that. This is the normal ResNet, and this is RevNet, and you can see that they do go through a lot more operations. Okay, the last one. This one has a lot of complicated math, so I'll just keep it short. You know what the usual attention score is, how it's calculated. I simplified it to just Q times K. We softmax it, and V. And what Performer does is that it simplifies the runtime operation of this calculation. usually we multiply q times k and then multiply that by v, and the time complexity of that is L squared d. And if you rearrange these variables into k times v first and then multiply it by q, then the runtime complexity decreases to LD squared. And usually the sequence length of a model is longer than the hidden dimension length. So this would be slightly less complex than the first one. But obviously we can't just rearrange this equation because we're limited by this softmax function, right? So the authors were like, okay, we're gonna replace it with we replace the attention mechanism with an approximation. I will not go into the math, but basically what k is a kernel function. And sorry, I need to open the speaker notes for this one because I don't remember everything. So k is the kernel function, and phi is a feature map. So in standard SVMs, there's a thing where if every kernel can be divided into two feature maps multiplied together, and then that simplifies the operation. And that's basically it. There's a lot of math that I don't understand that you can probably read into. The links, some helpful links are linked within the PowerPoint that you can look at later. And I think that's it. Yep, that's it for this presentation. Let me just so as always, do you have any questions?